Hello and welcome to SudoKanard. It's been a while since I did a test solve of a Sudoku puzzles I found on the Cracking the Cryptic fan server on Discord. And this particular puzzle is called Poisoned Little Killer, and it was set by SenatorGronk, and I don't think I ever solved a puzzle by SenatorGronk, whose nickname I found very tasty. So the rules are anti-king, meaning that two cells that touch diagonally must contain different digits, or same digits can't touch diagonally. So this is also called no touch or no touching on some, in some online contests. Now there are poison digits in the grid, and each box, each row and each column should contain exactly one poison digit, and they follow an anti-king constraint, meaning that poison digit shouldn't touch diagonally, so we can't have poison digits here and there. And we have little killer sums, meaning that each number in the margin is the sum of the digits along the mini diagonal pointed by the arrow, except that poison digits are not counted in those sums, which makes this, probably very difficult. So where should we start? And scanning the grid, I saw this 5, this 6, which would be absolutely impossible in a standard little killer puzzle. But this 5 would be possible. No, it wouldn't actually. The only way of making 5 as a standard little killer sum would be something like this: 1, 1 here, and 1 or 2, 1 and 2 in those cells. But this wouldn't work because 1 would be next to a 1 diagonally. So there has to be some poison digit on this diagonal. So I think I just do it this way. We don't know which one at the moment, and we don't know how many of them, but obviously there's at least one non-poison digit. And actually there has to be at least 2, because they can't touch diagonally. So we could have 2 poison digits in those cells, and something else probably. Now with those clues, anything could happen, but with this 5 clue, the minimum we could have 5, we could have 4 cells adding up to 5, or even 5 cells actually. 1, 1, 1, 1, no. For them not to touch diagonally wouldn't allow us to put 5 digits 1, I mean. So we need to have at most 4 real digits, meaning by real I mean not non-poisoned. Let's say 1, 2, 1, 1. And there are 8 digits, so we have at least 4 poison digits. At least 1 poison digit in here. And we know, no, that's not about the 32, that's about the 5. We know there are at least 5 poison digits, but they can't touch diagonally, so it will be at most 4 as well, because there are 8 digits. So that's exactly 4 poison digits along this diagonal. And something similar should happen with this 6. There are 8 cells along the diagonal, so at most 4 poison digits. And let's have a look. Oh, they cross here. So they may have a poison digit in common. So at most 4, but probably at least 4 as well. Could we have 6 as the sum of 5 digits? That's the question. 1, 1, 1, 1, and 2. We could have 1, 1, 1, 1, and 2, which would make 6, and then we would have 3 poison digits. So that's 3 or 4. Oh, I wrote ou, which is French for or. So 3 or 4 poison digits. But now, let's just think of this 5. This 5 requires, we have 4 non-poisoned. So there must be 1 plus 1 plus 1 plus 2. We have 9 poisoned 1 and 2 digits. So that's something very, that's a strong constraint. I mean, that's very restrictive. We know we have those digits not poisoned on this diagonal. And this should interact with what is possible here. But if we put a 1 here, it could work. Well, I entered those digits somewhat randomly, so, well, so about the poison digits, we already know we have 1 of them here, at least, exactly 4 of them here, at least 3 of them, but 1 could be common to those and those digits. We could have this common digit, and this could be a common poison digit between this and this. So this is actually at least, well, if we assume those digits to be poisoned and to be, yeah, if we assume them to be poisoned, we only have 6 of them. Oh, but, oh, this wouldn't work, actually. Now, that wouldn't work, I think, because poison digits must be in different rows and columns. So, how could we have them fit? How do we fit 4 poison digits here, 3 there, at least 1 there? If we repeat, now, if they share something here and here, I'm not sure it works. Because this is not available because of that. This place is not available, and we can't put them here. So we have only 1 here, none of them here, 1, 2. And 1 here, that's only 3. So that wouldn't work. We can't have them both. Can we have just this as a shared poison digit? So this is not poisoned. Let's say, well, this is not poisoned. I just mark it down with a heart. And So we have one poison digit somewhere in those cells. I put one here, but it could be there. And it can't be here, so it has to be here or there. So there has to be one. If this one is here, then we must have those digits, those poison digits. So this one is not possible, actually. What did I do? No, that's not, that's this way. Okay. If I decide to put one here, then those must be poisoned. Not sure about this one, could be here. Let's pencil mark those this way. Then, what about this? We can't have one here. We must have one here or there because of this 5. And I don't think that we can have 2, but not sure about that. Where do I put 3 in those cells? Because there is one here or there, I can't put one here or there. So having 3 would be here and there, and it would clash with those. So I think, assuming there's one poison digit here, I get a contradiction. So I can't have them both, and I can't have one here and not one there. Let's try the other way around, meaning let's try to put one poison digit here and none here. Well, we already know there's no poison digit here. And we must put 4 of them here, so actually I've removed this assumption for now. I just take for granted that I have proved that this can't be a poison digit, and then I must have one here and one there, and instead of dots, I just highlight the cells. So those are poisoned, and we know that this cell and this cell can't be poisoned. So I have to poison this one or this one. And this is not ruled out for the moment. And let's just consider those can't be poisoned. So one of them has to be poisoned. And if I put one here, then both cells here are not to be poisoned, which is impossible. So only those cells can be poisoned, here or there. And I'm starting to think that this one has to be poisoned, but let's have a look. If this one is not poisoned, then I must poison this one and this one, which looks possible, or does it? We still need 2 poison cells. Let's say I poison this one. So those are not poisoned. We need another 2 along this diagonal, and they can only be here and there. But now I also need 2 on this diagonal, and they can't be here or there, so they have to be here and there, and this one clashes with this one. So I think this proves that this one has to be poisoned and to be shared between this diagonal and this diagonal. Now I need 2 more. And they have to be those ones. Oh, actually, assuming this one was not poisoned led to a contradiction or straight away. I hadn't enough cells left to put 3 poison cells. So I need 2 more, on this diagonal. They must be here and there, and 2 more on this diagonal, so they must be here and there. Now it all fits. That makes 7 poison cells, and the remaining ones must be here and there. Now I think that's it for poison cells. Okay. Now I think that Sudoku may begin. And there are 2 poison cells here, actually. And let's have a look which sums are poisoned. Oh, those sums, 16 is not poisoned, 6 is really poisoned, 16 is poisoned. It has only 4 digits to take into account. Let's have a look at this 6. We now know that 5 digits are not poisoned, so they have to be 4 ones and 1 2. So those digits must be 1 and 2, and this one has to be 1. So that's this way, because ones can't touch diagonally. So this 6 now is fulfilled. So I highlight it with the blue color as well. Now those cells must add up to 5 without using a 1, so they must be 2 and 3. And they really are a 2-3 pair. This 5, we now know that 2 is here, so the remaining 3 cells must contain 1s. And now this 5 is fulfilled. Have we placed all the 1s? Not quite. There's still a 1 in this poison cell. And a last one in here. Well, let's say this 5 is somewhat fulfilled. This 16 needs all those cells, but that's not so constrained. This 16 is not so constrained either. What can we do now? Is there anything to do with this one? May be interesting regarding this 30 sum. Well, 5 digits with a sum of 30 are not so constrained as it happens. This 55 sum, this 55 sums includes a 1. So the remaining 7 digits have a sum of 55, which is really a lot. Of 54, sorry. Let's have a look at the maximum. The maximum would be with 8, 9 here, 9 here, 9 here, and this couldn't be a 9 because of the anti-king constraint. 8, 9. So the maximum would be 3 times 17. That's 51. And the 9, that would be 60, so 61. We have 7 degrees of freedom. That's a lot. So that's somewhat constrained, but not that much actually. Now, are we supposed to add up those 3 diagonals? That's a common practice on Little Killer. Let's just see which cells will be counted. The total sum is 70. And in this 70 sum, we have all 7 digits here, or 7 digits here, and 1, 2, 3, 4 other digits. And that is somewhat not very much, because let's have a look at the minimum value of those sums. Those 7 digits have a minimum value of all digits from 2 to 8. And I write it down in black because green is very light. And we know by sandwich Sudoku that this sum is 35. So that's already a lot. The minimum value here, it includes a 1, but it does not include both 2 and 3. So the minimum value will be 1 plus 2 plus 4 plus 5 plus 6 plus 7 plus 8. That's 7 digits. So we only miss 9 and 3. So the minimum value is 23. Is it really? Oh, I was mistaken. The sum is 80. Oh, okay. That makes more sense. Now, that's already 68 minimum for those cells, and we still have to take into account those 4 cells. This one has a minimum of 2. This one and this one can't be the same. This one can't be 2, so it has a minimum of 3. 3 will make this a 2, this a 3, and this could be a 2, so the minimum is 5 here. And 3, 2. And having 3 here will make this a 2, and this will be a minimum of 3. So the minimum value of all those highlighted cells would be 68. Would be 78, sorry. 35 plus 33 plus 10. It would be 78 instead of 80. So there's only a margin of 2, assuming I didn't forget anything. Well, that still leaves some room. But then, assuming this would make this a 9, and this a 9 as well, and all Poisson digits are different. So we can't have 8, we can't have all these digits not contain a 9. So actually one of them has one of those 8s has to be turned into a 9. So now we already have 69 plus 10, 79. So there's only a margin of 1. There's only 1 degree of freedom. So what do we imply by this? What is implied by this? This had a minimum of 3, and because of this 4, it couldn't be a 4, so this one has to be a 3, a real 3. Making this a 2, this a 3. Right. And now, oh, this is very, very nice. This 3 and this 3 acting together with the anti-king constraint rule out 3 from all those cells. And we can't have this be a 3 because this sum would be much bigger than 34, and the overall sum with those little killers would be much higher than 80. So this still has to be 8, 9, or perhaps 7. So 3 has to go here. 3 has to go in one of those cells, and this one can't be a 3. So it has to be a 2. We said it was at least 2, but it can't be 4 or higher because the overall sum would be too big. So this has to be a 2, and we know there's a 3 somewhere in there with a Snyder notation. This is really neat logic. I love it. What about those 3s now? There has to be a 3 here. Well, not sure about what follows. So we know that those must be 8, 9, or maybe 7. Where do we have some let's say, flexibility? Not really sure. What about the 2s? There must be a 2 in one of those cells. There must be a 2 in one of those cells. Oh, and about this one, we arrived at this, assuming this was a 2. And there's only 1 degree of freedom, which would allow this to be a 3, but 3 is not allowed. So this has to be a 2. And now, with those 2s and the anti-king constraint, this has to be a 2. Now we have a 2 somewhere in one of those cells. It might be this. And with this 2 and those, we don't have a 2 here. There's a 2 somewhere in those cells. Two in here. 2 and 2. There's a 2 somewhere in one of those cells. What else is implied by all of this? But could the 2 be here? Or we say there was, I said actually, I found out that there was a margin of 7 on this. So 2 is still a possibility. Or is it 8, 9, 8, 9? That would be 51 plus 2 plus 1. No, that wouldn't fit. 8, 9, 8, 9, 8, 9. No, because those must be different digits. That would make really 51. 2 wouldn't work here. So 2 is here. Now, no 2 here. 2 is in one of those cells. And because of those, we know that 2 can't be here. And 2 can't be here. So on this row, 2 can only be the poison digit in this cell. And now there must... Oh, and 2 can't be in another poison cell. So the remaining 2 is here. And 1 is here. Well, this puzzle is really, really great. I bet it will be featured on Cracking the Cryptic. Yes, it's really that good. What next? So we have all 1s and all 2s. And we're still not quite sure about what happens in all of this. But we have some digits on those diagonals. So I was thinking globally, but it may be a good idea to think more locally. how do we make this 18? The minimum here is 3 plus 4. Same here, 3 plus 4. So that would make 16, which is already very close to 18. We still have 2 degrees of freedom. So instead of 3 4 3 4, it could still be 3 5 3 5, or 3 6 3 4, or 3 4 5 4. Well, that's still 4 ways of distributing digits. Would 3 work here? I think it would. 8, 9 in those cells would make 51 plus 1 plus 3. That would make 55. So a 3 here would work. Oh. What about this 30? So if this is a 3, we still have this option of having 4, 5 here and 3 and 4. Yes, that would work. And how do we make 30 here? With 2, 3 and 1. We still need 24 with those 3 digits. 24 uses at least a 9, which is compatible with what we said about those cells. It could be, and there's at least a 9 in one of those. It's 9 and 8 or 9 and 7. Yes. Is it true? Not quite, actually. So I said one of those should have a 9, but maybe both of those sums include a 9. In which case, those would be... Oh no, if I make this a 9, then the missing digit is 8, and the missing digit is the poison digit. Same here. So one of them really has to be a 9, actually. And I could turn this 7 into 8 and have the poison digit be 7. That would work. But these could still be 9 and 8. And the different digits... Oh, we already know that 2 and 3... 2 and 3, that's 5. Oh, that's it. None of those can be 2. So the minimum case is actually with this. So a total of 69 here and 11 here. So those have to be 3s. So this is a 3. That's also a 3. And now we know that those digits must be 8 and 9 in some order. In some, well, in some way. And all that remains, well, all that remains is just the remaining digits, and it should work. So that's, let's have a closer look. This is 54, 55, that's 55, so that's 90 minus 17, that's 73. 73 plus those digits. No. Oh, minus 2 minus 1, so that's 70 plus 3 plus 2 plus 3 plus 2 plus 3, that's 80. Okay. So that's correct. Okay, so now we have 8 here, we need another 24 here, another 24 here, and another 16 here. The 24 with 3 digits is the more pressing, I think. Oh, or just the 18. Only one option did not use a 3 in here, it was this one. So we know we have 4 and 5 here. What? No. No, doesn't work. I can't have a 3 here. What? Mm-hmm. No, now this 18 sum is broken. The only place for a 3 is here. Ah. That's a very Bobbins moment. No. So there had to be a 3 in those cells. Ah. Oh, well. What did I do wrong? Now, there's no way around that without using the 3 here. No, there. That's a minimum of 20. I can't make this be 18. So what was the logic between putting all 3s here? The logic was really that those 2s prevented this digit from being... Oh no! There was some wrong logic going on here. These 2 that I removed was actually this one. So this one is confirmed. And what? So we now know that this can't be a 3. The uncertainty was about this being a 3. And we saw that... No. What did we see? Now, we saw that making this and these 3s wouldn't work. That's it. Because there has to be a 3 somewhere in those cells. So maybe I'm supposed to have a look at what happens if I put a 3 here. If I put a 3 here, then there can't be a 3 here, and there has to be 1 here. If I put a 3 here, then there's a 3 here, making those 4 and 5, and those 3 and 4. On the other hand, if I put a 4 here, then what? If I put a 4 here, then all this is the minimum case, but I still don't know where 3 goes here. I've removed this one, these 2. So there's still a possibility of having a 3 here with 9, 7 in those cells. But is 3 really not possible here? I think, what if I put a 3 here? Then we saw that this couldn't be a 3 because those would be 4 and 5. So we must have 3 and 4 here, and this becomes a 4. Now those must be 8 and 9. And that's 9 here. We need another 23 here and 24 here. And oh. By Sudoku we get a 4 here, and 4 here removes 4 as possibilities in those cells. So I was right, that was the impossible case. So that should feel a bit bifurcated, but not that much. That's a very nice elimination. So 3 has to go here. And now we have 5, we need 13. Which could still include a 3. And let's say 4 and 6 with a 4 here. So with this 3 and this 3, we get a 3 here. And there's a 3 here, but what about it? 16 here with this 3. And there's not that much room here. Actually, there's only one way of doing this 16. This is at least 5. So this is at least 5. And now, those digits now must have a sum of at most 8 without being the same. So we could still have 3 and 5. So that's an option. Could we have this be a 6? And then with 4 and 5 this would work as well. No, that wouldn't work. But with 3 and 4 this would work. And that's the only way it would work. They would have to add up to 7. And those are really the minimum values. So this is at most 6. So this has to be 5 or 6. And with 5, I say those would have to be 3 and 5. So this has to be a 3. With 5 or 4 here. So those are the only possible ways of having this be 16. What next? I think I need to do more logic, more arithmetics on this 18. Is it required to have a 3 here? Not really, because it could be this. But can it really be this? If this is this way, then this is a 4, and those are 4 and 5. And then this still has to be 3 or 4. which I can pencil mark. If those are 4 and 5, Oh, I was thinking one poison digit has to be a 3. Not here, not here, not here, not there. This could be a poison 3. This one could not, because of this 3. And this one could be a poison 3. So one of them has to be a poison 3. What is implied by that? If I make this the poison 3, then this is a 4. And so those must be 8 and 9. And I'm not sure what to deduce from that. Well, if this is a poison 3, then those must be 4, 5, and 7, which is somewhat interesting, but not that helpful, I think. This 18 should be the key. Oh, this 3? There has to be a 3 here. Or is it about the 32? No. This 18 has the most constraint. If this happened to be a 3, then we would have those add up to 10, which would leave lots of possibilities. And this is not what we want. We want restrictions. And where will we get our restrictions? Can we place another digit on this diagonal, which would restrict this 55? This one was nice, but it's not enough. Oh, I'm stubborn there. Some nice fact is that those digits can't be here and they can't be here, so they have to be in those cells. That's not a lot to work with, but I'm taking any deductions right now. And this digit is not here, it's not there, so this digit has to be in one of those cells. That's nice, but it won't help me. I was thinking, what if I put a 3 in here? It pushes a 3 there, in one of those cells, removing this 3, so there has to be one here, and by Sudoku we get a 3 here, and then by Sudoku we get a 3 here, so that's a 4, and now those are 4 and 5, so they need to be this way. This has to be a 4, this has to be a 5, and this as well. At this point it still works. Now this 18 is fulfilled. We know that those are 8 and 9, I think. This 4 has absorbed the missing 1 in this 80 sum. Oh, but no, that's the 4 trick again. It puts a 4 here which conflicts with this one. That's also a little bifurcating. Not sure that's the intended logic, but well, it gives me some progress. So 3 is not here. So the only place a poison 3 can go is this cell, making this a 3 and this a 3. And now we know by this 16 clue that those must be 4, 5, and 7 in some order. And 6, 8, 9 in those cells. This 16 clue is now fulfilled. And let's have a look. Now, this is a 3. So those must add up to 17 now. So one of them has to go up. Well, how does this work? So now we have a 3 here. So we know that those digits are 4 and 5. And this one is 4. So this 18 clue is fulfilled. We know that we have 6. Those 3 digits must have a sum of 24. One possibility would be 7, 8, and 9. What else could it be? It could be 9, 9, and 6. Except that if I make those digits 9, 9, and 6, then those poison digits can't be 9, and one of them has to be a 9. Because if both sums here... Oh, no, I said that both could include a 9, didn't I? No. If I make those sums both include the 9, then the 8 must be removed, and 8 must be the poison digit twice, so no. One of them has to contain a 9, and one of them only has to include a 9. One of those non-poison digits. So only one 9 is possible, making the remaining 2 digits 8 and 7. And it couldn't include no 9 because it would have to be 3 times 8. So those are definitely 7, 8, 9. And this one is also 7, 8, or 9. So that's a 5, 6 pair. Making this 11, 13, 16, 19. We need another 13 without using 4 or 5. So those are 6 and 7. all those little killer clues are now fulfilled. This is 8 or 9, so one of them is 7, so this is 8 or 9. This is 8 or 9 as well. That's an 8-9 pair. One of them is a 7. That's progress. Now on this row we still need 6, 7, 8, 9. This one can't be 8 or 9 because those are already poisoned, so this one must be 6 or 7. This can't be 5 or 4 because it sees both digits here, so it has to be at least 6. Five could go here. 5 can't go here, nor there. It could go here, could go here. I said 5, but I was thinking 4. 4 has to be in one of those cells. And I see no restriction. But this is not a 4. This is still not fully resolved, and this 55 sum still remains to be used, and I guess it will be used to disambiguate something in the later stages of the solve. Well, the solve is already somewhat late, so let's have a look. Those must be 5, 6, or 7. What else do we have? Five, and we still need 6, 7, 8, 9 on this row. We still need 4, 5, 6, 7 on in those cells. This one is 6 or 7. Do we have a restriction on this? Can't be a 4, so it has to be 5, 6, or 7. The interesting stuff is that if this is 5, then this is not, then this is 6, then this is 7, then this is 6. 5 makes this 7 and this 6, so those must be 4 and 5, which is compatible with those. Well, oh, that's standard anti-king logic. Those digits are 6 and 7. They see these cells, so this cell includes a 5. This one is 6 or 7. This one is the same as this one. In the same fashion, this can't be 6 or 7. It can't be 5, it can't be 1, 2, 3. So what remains? It could still be a 4 or 8 or 9. It could be the same as this digit. So 4, 8, or 9. On this row, 5 can't be here, it can't be here, so it has to be in this cell. Nice antiquing logic. Now those must be 4 and 7. On this row, we still need a 6. It has to be here. Now we know that 6 is not here, so 6 has to appear in one of those 3 cells, which is not saying that much. Five's not here. 5 could still be here. No, this 55 still can't be used. No. 6, 7, 8, 9 in those cells, but which one? Is there something weird happening with this? 6 would make this a 4, 6 would make this a 5, and this a 5 as well. So 6, 4, 5, 5. So 5 in one of them. What if, well, let's say this is a 5, and this has to be a 5. Oh, and it breaks, because this 5 and this 5 would put a 5 here, which would clash with this one. Okay, that was very well concealed. So this is not a 5, that's a 6. This is a 5. This one is a 5 or 7. This is a 4 because of this 16 clue, which is now fully used. We also get, because of this 4, we get a 5 here and a 4 there. And next, this 4 fixes the 4-7 pair at the bottom. Four here, 4. Only this cell can contain a 4 here, because this 4 removes the possibility here. And now we get a 4 in this cell. We must have a 4 here or there, and in one of those 2 cells. But which one? Only this can be a poisoned 4 now. And we get a 4 here. And we have all 4s. We're on all 4s, you would say. So that's some more progress, I guess. It's still going very slow, but that's really a difficult puzzle, undoubtedly. There has to be a 7 in one of those cells. But it's really not helping. There has to be a 7 in one of those cells, and a 6 and a 7 here. Yes, that's true. what is the next step? We still need 5 and 6 here. Do we? Oh, yes, so this can't be a 6. Yes, that's true. This 6 puts a 6 in one of those cells. So this is 7, 8, or 9. This can only be 5 or 6 because of this 7. So we still need, well, to distribute those digits in those 3 cells. Oh, and this sees at the same time those cells, so this can't be 8 or 9, so it has to be 5, 6, or 7. We still don't know much about this 55. Let's have a look. This can't be a 7 because 7 is in one of those cells. So it can still be 6, 8, or 9. This deserves a pencil mark, I guess. This is 7, 8, or 9. This is 7, 8, or 9. Because a 6 here would clash with the 6 in one of those cells. There has to be a 5 in one of those cells. And in one of those 2 cells. There's no 5 here, no 5 here. One of those 2 cells together with 5 in one of those. Where can I find some more elimination? Oh, 5 and 5. There's one here. There's one 5 here. 7, 8, or 9 in this cell. What next? 7, 6 here. So this is 8 or 9. Still not that much. What? Progress is very, very difficult at this point. I get the feeling, oh no, 6 has to go here. This can't be a 6. That's a 5. That's a 7. And this is a 6. So now, what do we get? This is not a 7. This has to be a 7. It pushes 7 in this cell. No 7 here. These 2 cells must be a 6, 7 pair. And that's not a 5, so it has to be 8 or 9. 5 can only go here. This is 8 or 9 as well. Now this is not a 5, this is a 5. with 6 or 7 at each side, 8 or 9 here, 6 or 7 here, 8 or 9 here. So this is 17. 6, 8 or 9 here. I guess the 55 will really be there to disambiguate. This is not a 7, so it has to be 8 or 9. There's a 5 here. There's a 6 here. That's not a 6. That's a 6. This one is not. This one is. Will we get the remaining 6? That's a 7. That's a 6. That's a 6. That's a 7. That's a 6. That's a 7. And we get this 6. This one is not. That's a 7, I guess. No, I'm not guessing. I prove that this is a 7 because of this one. 8 or 9. 8 or 9. This one is not a 7. That's a 7. So we are left with all 8s and 9s. And we have to disambiguate, and this is where this 55 comes into play. That's 17, 24, 31, 37, plus 18. So those are both 9s. That's an 8. 8 here, 9 there, 8 here. Just hope it will work. So it has to be a 9. I hope there won't be any conflict, any anti-king conflicts. And that's it. It seems to be really working. So that was some journey. That was really at least a 4-star puzzle in terms of difficulty, perhaps even closer to 5 stars. It was really, really difficult, but very, very well set. Excellent puzzle by SenatorGronk. So thanks for watching this test solving video. It was really a difficult puzzle, but a very nice one. I know I'm repeating myself. So see you soon on SudoKanard.